Our final speaker for this session is Professor Torsten Hoefler, professor at ETH Zurich and director of the Scalable Parallel Computing Lab, who is also an ADIA Lab fellow. He has featured at both of our previous symposiums and also ran a seminar session this year and joined us for the summer school. Today, Torsten is asking the question, can we build an AI climate scientist? So prepare yourselves to learn more about groundbreaking advances in global simulation and how combining physics-based modules with AI can accelerate our understanding for the Earth processes. Thank you.
Thank you very much, Fatima. Thank you very much, everybody. So my first question is, who has been here at the first ADIA Lab Symposium? Who's been here at the second? Okay, so there's about 20% of the people who've actually been here before. And I already saw that my time has been cut by 30%. So I'm going to speak extremely fast. Actually, if I'm going to speak faster than the speed of light, then we'll make it on time for lunch. But I want to ask the question that is following up the two talks I gave before. So the first 3 minutes of the talk was planned to be 5 minutes. It's going to be a repetition for those who've been here, but I want to bear with you because the other 80% in the room have not seen this yet. So can we build an AI climate scientist? So look at this little figure there. Imagine if you want to see a real-life person, imagine that's Björn. That's the climate scientist who's trying to predict the future and to tell us what we should do with our wonderful Earth. So now, and if that would move, so now we all know that we're living in an environment where the Earth is warming, so no problem. I don't have enough time to have this play and tell us all these things. But I want to quickly recap the thing that we've seen 3 times by now, so it's going to be very, very fast. Spatial resolution on this x-axis, and we resolve more and more processes. So we all know this, we've seen this before. So we have continental scale, cyclone scale, storm scale, and the cloud scale that Björn was actually talking about, which is the goal now that we are going towards 100-meter resolution, which is extremely crazy if you think about the requirement. Actually, if you look at this red bar is the weather resolution that we're simulating in Switzerland today. And actually, if you look at this looks pretty good. So this is an animation showing a specific weather event, which is great. You can see where I'm living. This is where all these clouds are, and it's much nicer here. And so this shows a non-interpolated version of the actual simulation. So every pixel there is a simulated point. So it's an extremely high resolution. Unfortunately, that's about 1/6000th of the Earth that we can afford to simulate in real time, and we have a pretty sizable machine to do this. So that doesn't help us if we want to talk about climate, global climate, especially not for 30 years, because we are only simulating a couple of days here. Okay, you can see the required storage for just one weather trajectory with all variables with this resolution. So we have 50 petabyte on the site. And then what we also learned, weather is a specific event. Climate is the distribution of weather into the future, so we have to simulate many, many, many specific weather events. So the single simulation is here. This is called ensembles. And now if we look at the number of ensembles can go to thousands. We can simulate a very coarse resolution with a very small number of ensembles today with our laptop, absolutely no problem. If we increase the compute power, we can either do more ensembles or we can do higher resolution. We know that. The Levanta machine that Björn talked about is there. We can do a single simulation with a 5-kilometer resolution at 1 simulated year per day. That was on his slides. We can go further. We can build bigger and bigger machines. We can get to 1.5 kilometer on the biggest machine we have today. Outside of this, we cannot compute. And again, this is a repetition. We should all know this. ETH was an event where we had a couple of years ago. Both Björn was organizing this, and Peter was there. Many, many people were there. I think Stan, you were also there. We discussed we want to get there. Outside of our current range, we wrote a technical paper of how to achieve this. We could do 2 things. We could either build faster computers, which we've been done the last 40 years, so this is great. We build faster and faster computers. Or we could use machine learning, like Peter was just proposing, to break through this. So those are the 2 fundamental things. So now how is the AI revolution going? We just talked about machine learning. Last month I was in an event that's called the Heidelberg Laureate Forum. It's a meeting where all the laureates of the biggest awards in mathematics and computer science meet and discuss things. I was honored to speak there. Sanjeev Arora was also speaking there. He's a mathematician. He got the ACM Prize in computing and math. And he talks about a math superintelligence. And he actually says that AI will probably replace mathematicians. So one of the top mathematicians in the field says AI is probably going to replace mathematicians. Everybody was shocked. The meeting was kind of going into depressing mode because all the young mathematicians in the room were sitting there and it's like, oh my God, what am I doing? Then the next person goes up, David Silver, one of the co-inventors of reinforcement learning, got the ACM Prize in computing a couple of years before that, and basically says, well, a similar thing. So the future of AI is going to replace a lot of capabilities, amend a lot of capabilities what we humans are doing. This was all about math. But now my question is, and I did give this talk at ADIA Lab 2023 where I said computation is the new oil. Today it's clear that it is. And today it's absolutely clear computation is the major resource that humans are using to advance humanity, right? So that's what we heard. But now the question is, well, there's this AI mathematician, but can we build a little AI climate scientist? Well, this is harder than building a mathematician, actually. I'm not saying that climate scientists are harder to replace or anything, but this is harder because it's such a multi-structural problem. Because if you look at the fields of human knowledge endeavor, going from sociologists on the very left to mathematicians kind of like very far into the right, if you arrange these fields by purity, math is a very pure field. I have proofs, I have ground truth, I have axioms, I have strong theory, I can prove everything. A machine is very nicely dealing with this. On the very left side, sociologists, oh my God, don't get a machine started on sociology. And somewhere in the middle, we have these chemists, biologists, physicists, and the climate scientists are in that group. It's somewhere in between. It's not a rigorous field like math is. You cannot prove things especially about the future, but you have some foundational physical principles that you deal with. And this is exactly what we've been discussing in this forum here. AI on the very left, maybe, and things, mathematicians on the very right. So let's go a little bit more into detail on this. What does that mean? And again, I want to give us an axis here of how we could use artificial intelligence to answer scientific questions. This is broader than climate sciences, but I wanted to discuss that here because I think it fits very well. On the very left are empirical sciences. Sociology is one of the most empirical sciences you can imagine. You study people. People don't have a mathematical underlying concept, at least most people, many people don't, I don't, I hope. On the very right, we have theoretical sciences where we deal with axioms and basically man-made understanding of nature, physicists, very deep physics. So now, on the left side, what I call the empirical science is basically uncompressible knowledge. This is very much the art of dealing with people, the art of dealing with societies, the art of dealing with finances, for example, is in this area, because the stock market is largely driven by public opinion. And then on this we have, for example, a large database, the public medical database. All of medicine is very much uncompressible. There's a very small number of foundational things. Compressible knowledge on the right. We have all these equations. These equations are absolutely wonderful. They drive society. These equations we can write down in a couple of characters. Absolutely ingenious. Now, on the left side in empirical sciences are, for example, medical diagnostics, clinical practice guidelines. How do we treat humans? How do we treat us when we are sick? There is no real deep science to this. There's no theory to this. There's lots of observations. I give this person this drug, person dies. Oh, not a good idea. Maybe try some other drug, right? This is what people have done over decades, actually over centuries. Then we go into biomechanical analysis. Now we simulate humans. I'm in a scientific project where I work with health scientists to build a foundation model of the human body. We can do this. We can simulate bones. We can simulate bone structures. We can simulate how hips break. Very, very big problem, actually, in many societies. Then comes weather forecasting in the middle, which is now, again, we are working with these simulated environments. We are working with physical equations, but we apply it to a system that is too complex to be actually modeled at the greatest extent. We try to increase the modeling fidelity by increasing the resolution, but at the end there will always be the butterfly effect that will mess us up to some extent. Climate prediction is a little bit further to the right, because in climate, since the horizon is longer, this butterfly effect plays a longer role. Like as Björn said, when we roll down the marble, the earth marble maybe, down a hill, the further it rolls, the larger the uncertainty, the bigger the importance of theoretical fundamental understanding gets. And then we have structural mechanics. Many of us know this. This is how we build cars, oil rigs, and things like that. This is wonderful because this is very structural, very close to his deep theory. At the end, we model all of this. As humanity, we model all of these things. And when we use modeling, we typically improve capabilities to the left, better prediction, and we have complex models there. And we invented these data-driven representations. And actually on the right, because we have models, we don't need to improve capabilities. These models are near perfect. We just usually approximate them to make them faster, because as we've learned from both Bjorn or everybody who was speaking here, we have a computational problem in climate sciences. We have the models, we can totally do it, we cannot do it fast enough, so where we approximate it. And this is then model-driven representations on the right. So now where does our AI climate scientist come into this game here? Well, the AI climate scientist could actually take advantage of this modeling by combining traditional machine learning and AI, something that, that Peter was talking about, basically on the data-driven side. So we use these models basically as they are without much additional physical inputs. All of the models that are in production today, they have basically zero physical prior in them. They're data-driven models. And as Peter said, it took a while to trust these models. We trust them because they have over and over and over again delivered. It's not because we understand them. No. We don't understand what they do. We've just seen in the past that they've worked well, and so we trust them in the future. How do you trust another human? It's the same thing. It's called building trust. You do not understand the human. You don't have a fundamental reason why you should trust any other human. You build that trust through experience. And this is what we did on the left side. On the right side, it's very different, because there we have a fundamental understanding of what's going on. At least we believe so. By the way, the funny joke about the physicists with the Nobel Prize is a physicist gets a Nobel Prize for inventing a new phenomena or for discovering a new phenomena, and then the next physicist gets a Nobel Prize for proving that that phenomena wasn't actually right. Like, look at the Niels Bohr, for example, with the nuclear model that atoms cannot be split, and then they oh yeah, by the way, they can be split, and so on. And so this is another thing where we may or may not trust these simulations, but at least they have a very high confidence that they work. And now AI for climate, we need to work on both sides. We need to use traditional machine learning and AI and traditional modeling and simulation and put them together, and not use pure data-driven models. They work really well for weather. For me, weather is a solved problem, actually, because in weather, we already perform better than the physical models. So it's done. You need to operationalize it, it's all great. In climate, we don't. In climate, we don't. In climate, we need to combine the two. Okay, wonderful. So how do we now do this? I want to use my last couple of minutes, and I'm actually really operating at about twice the speed as I was planning on, to give you a little bit of an overview of what we've been doing in order to do this. And I may not be within the 30% cut version. I may go 2 minutes over, I hope. I hope that's okay. So we were talking about data, compute, and models. And now let's talk a little bit about data. So about data, we mentioned that the data is incredibly large. Actually, an exabyte we have at the ECMWF. ECMWF said that they're producing 1 petabyte of simulation data per day. The NASA is collecting more data from the satellites that they can actually store. So we have a huge data problem, because also storing data is very expensive. So we have developed a method that we call statistically lossless data compression. It's not lossless, but it's statistically lossless. What does that mean? So what are the statistics of the data? Every sensor has an error. There's always a natural noise in the data. This is why in climate simulations we always run multiple trajectories, and they're slightly different. These are these ensembles. And what we do through these ensembles, we basically get a statistical distribution of what is going on at each point, at each time point, at each physical point, at each time point on Earth. What do we mean by lossless? We now take the distribution of each point, at each spatio-temporal point, and do the point-wise statistics, and basically find out what is our allowed error bound. So now, the philosophy is that we don't need to represent the data more accurate than we can actually measure it in the first place. Right? We don't need lossless compression, because that's all kind of stupid noise. So we need statistically lossless compression. And then we use a data compression mechanism where we combine existing schemes that I wanted to explain in more detail, but I can't, but doesn't matter. We find a residual. We basically find what is not compressed well, which points are falling outside my error bound, my statistical error bound. Then I'm taking the error bound in. I write a compressed bit stream, and I repeat this thing iteratively until I have a statistically lossless compression. And then I can guarantee that at no point in time my compressed data exceeds the confidence bounds that I'm defining on my ensemble. So this is great. Key idea going to be published very soon, blah, blah, blah. I mean, we minimize artifacts and enforce a strict bound. I can show you some comparison points here. So there are many other papers that do the same thing. Some are not error bounded. The short message here is that we are outperforming all of those significantly, and we are supporting the exact same error bounds that they do. They don't do the statistical error bounds as we do, but it doesn't really matter. We are competitive in terms of compression and decompression throughput, so we can actually use this in practice. The intuition, and again, I have to cut this a little bit. The intuition is really that and I don't have a pointer. I do have a pointer. Oh, it doesn't really work though. The intuition is that our scheme actually clusters the errors around 0. Other schemes like the SZ scheme, they use the full provided error bound, which is 0.25. No, it's actually here, I'm sorry. That's minus 0.05 to 0.05. And so you can see, well, if I had more time, I could explain this in more detail, that we're actually reducing the weight of the overall error while staying within the error bound. Okay, if you're more of a visual person, this is the compression, this is the original compressed field. This is a 100 times compression. You see basically no difference on this low resolution screen. Other compressors have the same error bound, and you can see artifacts that are basically developing here. Okay, wonderful. So we know how to compress data. This is actually also, I would say, the 100x is kind of a solved problem, so we can do it statistically lossless. Well, 10 to 20x, but in the lab we have 100x as well. So now going to the compute. So compute is actually complicated because the Earth system is really the most complicated simulation target that I've ever seen. It's more complicated than brain sciences because it has many, many more moving pieces than just a couple of neurons. It has varying scales, millimeters to thousands of kilometers, seconds to decades, and all kinds of things. For example, these things are the atmosphere, the land, the vegetation, the ocean biogeochemistry. I didn't even know that such a word existed before I talked to Björn. And anything less, and people like Björn tell me, anything less than that is not a realistic system to be simulated for climate timescales, because the vegetation may change. There may be deserts blooming if there's enough water. There's desertification going on if there is not enough water. So things change over time, and they drive an overall cycle. So at the end, the tool that Björn talked about is 1 million lines of Fortran. Right? So that's the simulation tool, 1 million source code lines of Fortran. And what we did in a collaboration with Björn is we actually ran this thing on a rather complicated architecture. Funny enough, what I'm going to tell you now in the next 2 minutes from a technical perspective was featured in 2 talks from a higher level perspective. So I'm going to give you the technical background to what happened in the 2 identical graphs both Stan and Björn had on this landmark achievement of 154, it's actually not 83, the latest result is 154 simulated days per day. So the idea is that we map all of these different components to the heterogeneous architecture, which is a mixture of CPU and GPU, and we really run them at the same time. And the insight is that we use OpenMP as a programming model on the left side on the CPU, and OpenACC as a programming model on the right side. The little success of my lab here is that we actually contributed DACE, the data-centric parallel programming environment, which made it 20% faster compared to the fastest OpenACC version that we could see. 20% is a huge number if you have that large cost. But now, what are the degrees of freedom? If you're a machine learning person, we always talk about number of variables, the number of parameters. Right? You've heard 100 billion here and 1.8 trillion there, and up and down. So we can do the same thing for weather models. How many parameters are we actually tracking in the model, actually climate models? So here, 347 billion is at 1.25 kilometer resolution is just the atmosphere. 2 billion is the land, 23 billion is the vegetation, and we have a time step of 10 seconds. On the left side, the ocean is 86 billion parameters, and 326 billion parameters is the ocean biogeochemistry, because there's so many different things to track in the ocean that you need many, many variables to model those. So now and it's a time step of 60 seconds. We already see that this is a large number compared to the numbers we heard in AI models. Actually, we have a total of 780 billion FP64 variables. Okay, we heard of 1.8 trillion, but it's not a public number, and I didn't say that number. So this is actually more bits than the largest public AI model, and it's also more bits than the 1.8 trillion parameter model, because we do all of that in FP64. 1.8 trillion parameter model is in FP16 most likely, so it's 4 times less. So we run, this simulation is not just is larger than the largest AI model that we are training, okay, in the number of bits. And we run it 2.4 times faster than the fastest run today at 145 simulated days per day, including all of that stuff, this ocean and biogeochemistry and whatnot, which literally comes for free. So I could now show you an animation thanks to Björn's team, but I want to skip this. This is a Gordon Bell finalist that Björn also mentioned in his slide, actually Stan also mentioned in the slides, that is coming up to compete at the supercomputing conference actually next week or in 2 weeks. Cool, that's compute. And at the end, models. So how do we get to models? I'm actually more or less an AI person by background. I care most about LLMs, climate science. I do as a hobby, so to say, working with great people like Björn and Peter, and then hopefully collaborating more. And so I'm really in the role that Stan was in as a helper scientist to support these people to achieve more, as an expert in AI and computer architectures to run very large problems. So now, what can we do to help there as a non-expert? We basically can look at the code. This is the icon code. This is a climate simulation. It has all these things, all these different components, as you can see: radiation, ocean, biogeochemistry, cities, and economy. You could plug in vegetation and what so. Now let's imagine we want to replace one of those components, the radiation component, for example, by a deep neural network. We want to replace it with AI because we don't want to, we believe it's going to be better or faster, one of those two. And we also want to replace the vegetation neural network because we believe we have a better AI model. So what I'm advocating is to use simulation together with AI in a single code. But now, you cannot just replace these components. What you actually want to do is you want to learn from observation end to end with model predictions that you compare with real observations. You compute your gradients, and you compute your loss function like you do in any AI model. What this requires is that you actually can do the derivative of the loss with respect to the input for all of these. And you have to do a local weight update for all AI components in your model while backpropagating through all these other components, right? So this is really annoying. If you have a 1 million line of code, Fortran code, you need to backpropagate an end-to-end loss through the whole thing. Basically impossible today, like does not work, period. People have done a hack in the past, so we really need backpropagation gradients. And here I want to also say that DACE can do this, the thing that we are developing in my group. So now, what does this mean? So we can take the input program, we can run it, and again, I don't have enough time to explain all of this computer science stuff. We can basically do the backpropagation at the mathematical level. Now there's this very interesting paper that Stan also mentioned, the neural GCM. They did the same thing, but they did it the other way around. They basically said, well, you know, we have an AI model, we want to couple a simulation to it, so we write a simulation in some kind of AI language to do this. They wrote a not so good simulation. If you ask them themselves, they say, yeah, it's a very basic dynamical core. It's kind of a prototype. It's a very small core, and they wrote it in a framework called JAX. Right? Just use XLA. That's what JAX stands for. It's kind of a silly name if you think about it. Nobody knows what XLA actually is, but I could explain it, but I don't have enough time. So upshot is that we are faster than that thing. Okay, so again, not enough time. So we have a 50% speed up. We are actually, in the geometric mean, we're actually 7.1 times faster for some codes, and GPU accelerated codes 8 times faster. So JAX is not very performant. JAX is for convenience. For these codes, Björn even mentioned for unstructured grids, you can actually do it, but it's really, 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 really slow. So we can do it, great. So that kind of concludes the idea. Now large-scale data. Can we now combine all of these three things to build an AI climate scientist? But that's something I want to leave open for the audience to discuss. So I believe in the far future, yes. And I just want to flash some slides, basically, and end my talk only 2 minutes over the 30% cut version here. Thank you very much.
Thank you, Professor Torsten. Any questions? Yes.
Thank you so much for presenting fantastic slides, and the way you articulated all the topics, I really enjoyed.
Thank you.
In many of your slides, you made us very upset, and in many of your slides, you made us very hopeful. In one of your slides, you mentioned AI is going to replace psychologists, physicians, including mathematicians. This is a very horrible thing when somebody explains human is going to be replaced by AI.
Yeah.
And this question, whenever we go in any conference, we talk about the AI, definitely this question come. My question to you is, by when AI is going to replace human? Human means these jobs like engineers, mathematicians, doctors, and if AI will replace them, then what they will do?
Yes,
Thank you.
this is a great question. By the way, this is not the first time that computers have replaced human labor. In fact, if we go back about 100 years, there were people that were called computers. Here I have a small disagreement with Stan. He said the fastest development is in the last couple of years. In fact, when people were replaced, the people that were called computers were replaced with real computers in the 1920s, 1910s. These were doing weather calculations manually. Right? These, and mostly women at the time, because they were more patient to perform these calculations and better at it, they learned to be real programmers. They up-leveled. They went one level higher. There's a wonderful movie about this. It's called The Hidden Figures. I highly recommend watching that movie. 9 years old, very, very good. It shows how people replace themselves with machines. This is exactly the same what's going to happen. We are going to learn how to use computers. We are going to up-level. Instead of programming, which is a very menial task, it's very boring, we are going to become designers. We will tell the AI what the AI is going to do for us. And like we don't multiply large numbers manually with paper anymore, which people did in the past, really bad job, right? That's like really boring. We won't program anymore, but we will do the next thing. So we will simply discover new jobs. I'm looking very brightly forward to this future, very much like with the mathematicians. The mathematicians are very often employing boring tools to solve their problems, step by step for doing proofs. Not necessary anymore in the future, like they don't multiply large numbers or add large numbers on paper. So we will just move forward to be designers. And this is going to be an awesome future where we will have jobs replaced, but many new jobs created, and more new jobs created, in fact, by that up-leveling of society.
Thank you, Professor Torsten, and for closing the session with such a visionary perspective on the future of climate modeling. That's a wrap-up of our breakout session. We now invite you to join us for lunch at the atrium before we reconvene at 2:15 here. But before that, can I please ask you all to join me in a round of applause for our incredible speakers today? Thank you.